1,200,000. Over 1,200,000 monthly riders are unsatisfied with London Transit's daily commute timeliness, their transparency, and their communication for arrival and departure time discrepancies. Hello, my name is James Morales, and today I am joined by Luis Del Tavo, Jason Adams, and Brody Smith, and we are presenting London Transit Delays, our solution for empowering riders with timely data. Now for some background as to why the need for LTD. Given the complexities with pulling accurate and timely traffic data with relevant impact on delays, there have been solutions that have come up over time. For example, there is the London Transit Watch app, which shows delays of traffic flow but fails to show delay factors. Then there's the very well known Google Maps, which shows London Transit's delay detour information and uses historical times to estimate ETA. Now, given the limited solutions to providing transparency to riders, we found that there is an unexplained gap between prediction and reality, which led to riders' frustration. It's for that reason that LTD is taking a bottom-up approach on focusing on delay factors and revealing these to the daily commuter. Now, as for our approach, we are focusing on primarily sourcing relevant data from news outlets, weather sources, and more, and then to centralize and transform this data in order to pull valuable insights from them, and then to finally display these insights in a comprehensive dashboard with an emphasis on transparency and timeliness.
Hello, my name is Jason, and today I'll be discussing the functional requirements. Data aggregation involves collecting traffic feeds from web APIs, which provide live traffic conditions across London, Ontario. We also gather weather data from reliable sources to anticipate how adverse weather impacts transit. Additionally, public events data from local calendars highlight when and where large gatherings might disrupt transit routes. For data centralization and storage, we use a NoSQL database to store all aggregated data, ensuring quick and efficient access. This approach allows for fast data retrieval, supporting real-time insights on the front end. The data visualization platform is designed to be accessible and interactive. It includes a map overview for spatial awareness of transit delays, category overview to help users quickly identify delay causes, and user interaction capabilities that allow exploration of specific areas or delay types. Data filtering and searching features allow users to filter data by category, such as traffic or weather-related delays, and search for specific areas, making it easier for users to find the information they need. Finally, we provide user documentation and onboarding to support users as they navigate the dashboard. This includes step-by-step guides and helpful tips to maximize the dashboard's usability. Since we haven't started Sprint 1, all user stories currently reside in the backlog. Sprint 1 will focus on foundational elements like data integration and initial setup of our data visualization platform. Priority for this sprint will be creating a functional prototype that aggregates traffic, weather, and event data into a centralized NoSQL database and visualizing initial insights. For Sprint 2, which is also still in the backlog, our focus will be enhancing the prototype with added interactive and accessible features. We'll deploy the dashboard to a server, improve data filtering capabilities, and add a backup/recovery system to ensure data reliability. This backlog includes everything we need to complete to ensure successful project delivery, from coding and testing to compiling reports and creating demo presentations. As we progress through each sprint, we'll also allocate time for documentation updates and any necessary preparations for project demos. This backlog keeps us on track toward building a fully functional and well-documented project.
Hi, my name is Louis and I'll be discussing the non-functional requirements. Here we have performance, usability, fault tolerance, security, and maintainability. Performance refers to our dashboard being browser-based and no installations or downloads are needed. It must be able to handle high load, allowing for users to easily access our dashboard with no delay, and it must be able to handle an increase of load relative to our data. Usability means that our dashboard should feel intuitive, not just on browser, but on mobile too. The display should be organized in a way that effectively displays our data. We must follow and conform to the standards set by W3C and allow for accessibility to those in need. Fault tolerance will allow us to recover lost data by performing regular data backups. We will also install a disaster recovery plan in case of failure. Security will be ensured by following best coding standards, preventing the system from attacks. If there are input fields, we will implement input validation. This will also prevent common attacks. And since most of our data is public, there will be no confidentiality outside of the models and insights we've engineered. Lastly, maintainability. We will ensure the codebase is easy to update and will reflect changes on the dashboard. We will also use a modular codebase so that these updates could be made without unintentional results. Finally, we will create unit test cases, end-to-end test cases, and integration tests. Here is our use case diagram. As we can see, we have two primary users, the transit user and the admin, which will have additional features such as manage user permissions, monitor data health field, manage data sources, and system maintenance. The admin will have all the features and use cases that the transit user will have. For example, receive real-time updates, filtration, real-time delay map, and much more.
Next, we'll describe LTD's system design. The ultimate goal of LTD technically is to produce a robust system with high reliability, extensibility, and maintainability. This is a high-level system architecture diagram. Starting from the top, data sources are a central component of LTD's mode of operation. They yield real-world situational data that can be correlated to each other using situational data in the form of statistical relationships to generate insights about what may happen in the future. Three subsystems exist to gather, relate, and display this data: the Data Ingress and Transformation System, DITS, the Regional Delay Prediction System, RDPS, and the Risk Visualization System, RVS. Each data source provides an interface which is bound by the Data Ingress and Transformation System. This system is responsible for obtaining information from data sources. To accomplish this task, DITS uses stream listening and scheduled polling, adapted on a per data source basis. After obtaining data, DITS transforms this information from protocol-specific responses into normalized situational data objects. It then writes these objects to the NoSQL document database. This database is a central connector for all three major systems composing LTD. The risk delay and prediction system is the next step in the data pipeline. RDPS utilizes current and historical situational data objects stored in the database to generate a future delay risk prediction model. It relates the situational data together through polynomial regression, which is a common statistical method for creating accurate prediction functions for nonlinear relationships based on features of the input parameters. The output from this function is a real valued number called the future traffic intensity. Depending on the geographic region, delay risk varies, which is why the city is stratified into small regions called tiles. Seeking to characterize the intensity of congestion in that region, each tile has a specific number associated with it, which is called the tile congestion multiplier. The higher the multiplier, the more susceptible this region is to traffic delay. The tile congestion multiplier is determined through historical data. Future traffic intensity and the set of tile congestion multipliers are related together and normalized, yielding regional delay risk, or RDR. Situational data changes frequently, so regional delay risk prediction is calculated at regular intervals, which are controlled by the scheduler. After each iteration, the regional delay risk prediction and the risk factors responsible for that delay prediction are packaged together into a single object called a risk profile. These objects are written to the database where they're consumed by the Risk Visualization System, RVS. RVS continuously reads the risk profiles written to the database and visualizes them into an information dashboard that's available to the end user. This dashboard is composed of adjustable tiles of varying presentations. Information is fed to tiles through adjustable queries to the NoSQL database, which can be set and changed in the data source manager. The combination of tile configuration and information configuration are stored as a dashboard definition. RVS makes this dashboard available through a web app frontend. Because LTD integrates together such diverse data sources, scalability and modularity are key drivers for system design. The same is true for LTD's class structure. Core objects are defined in the LTD common package. This package is used throughout the main systems of LTD. Domain-specific data format objects exist here, shown on the left side of the package. GTFS, GTFS RT, weather, and traffic data are the fundamental data types used in data transformation. On the right, the database client class is defined. This is a standardized wrapper class used throughout LTD to guarantee uniform access to the NoSQL database. Next is the DITS class diagram. On the top half of the diagram, various transformation classes are defined. All of these classes implement the transformation interface, which you can see in the middle of the diagram. Objects of these classes are responsible for making the conversion from raw data straight from external APIs into the domain-specific objects defined in the LTD common package. In the bottom half of the diagram, the data source interface and its children are defined. The retriever class, on the left, is responsible for polling a given data source at a specified frequency and converting responses into domain-specific objects. Similarly, the listener class, which is on the right side, is responsible for continuously listening to a data source. The listener will convert the bit stream into discrete domain-specific objects. Both the retriever and the listener class write these domain-specific objects to the central NoSQL database. Which class is used to get data on each specific data source is determined by that data source's specific requirements, as shown earlier in the system diagrams. Finally, these are the classes composing the regional delay prediction system. In the middle, the regional delay prediction class orchestrates delay prediction subfunctions. It also manages data exchange between the tile characterization related objects on the right of the diagram and the classes related to polynomial regression in the left of the diagram. The polynomial regression class is responsible for the execution of the polynomial regression process. It produces a polynomial function object, which is just the programmatic representation of a polynomial function. Data is written to the database with the database client class, just like the DITS does.
Our development tools consist of Grafana for the front end and the dashboard, TypeScript as the primary development language when creating API requests, and it will be the primary language for the backend. MongoDB will be used as a NoSQL database to hold our data. This will be the centralized database. Docker will be used to create instances of MongoDB and Grafana and keep a consistent environment for all of us. We will also use Docker to run scripts, allowing us to consistently pull data from MongoDB into Grafana for real-time updates. GitHub, Confluence, and Jira will be used for continuous integration and continuous development, CI/CD. This is our UI mockup. On the top right, we have a heat map showing traffic congestion of roads next to Western University. There's also other metrics like seasonal patterns, weather impact, daily news, passenger load per stop, and more. As you can see, we aim to make our dashboard real time, which is why the values here are always fluctuating. I hope you enjoyed our project walkthrough, and I thank you for listening.